So the contents of the webinar, I'm going to go into a little bit of simulation history. Where does finite element analysis come from? And specifically, where does SOLIDWORKS simulation come from? Talk a little bit of simulation basics as well. Then we're going to go into SOLIDWORKS and talk about designing with simulation. So the part that you see on the screen, this suspension component is one of the ones that, or is the one that we're going to be modifying and utilizing. We're going to talk about a summary and then again the question and answer section. So I just want to talk a little bit about the history of finite element analysis. It did start in the aeronautical engineering sector, and it really came about hand calculation wise right around 1941 to 1942. Then throughout the 50s and 60s, finite element analysis grew and developed at two main universities. And the only reason that I bring this up is because between those two universities, specifically Berkeley, that's where SRAC or SOLIDWORKS simulation started, was at Berkeley University. So if we look at the history of SOLIDWORKS simulation, 1985 is when SRAC, or Structural Research and Analysis Corporation, was founded by former Berkeley and MIT professors. Many of you, if you've seen the older branding, it was called Cosmos, was the finite element analysis package. 1995, SOLIDWORKS was founded. So before SOLIDWORKS, everything was done in a Unix-based system on a specific CAD station or a specific analysis station. With the introduction of SOLIDWORKS, everything was brought to a Windows-based desktop. And very quickly, SOLIDWORKS recognized the fact that they needed some type of an analysis package. And in 1998, SRAC partnered with SOLIDWORKS. They became what we call a gold partner, the first gold partner. And what that means is simulation is fully integrated into the SOLIDWORKS interface, and we'll show that a little bit later. And then as of 2012, 98% of the original Cosmos code, and this should tell you a little bit about how robust that original code that was developed between 1985 and 1995 really was, because we now have 98% of that original code adopted into SOLIDWORKS. So let's just talk a little bit about simulation basics. And you see two parts on the screen. One is a very simple square tube, and the other is a little bit more complex casting. If you've been through the Essentials class, you should recognize that part. But essentially, hand calculations on beams and cylinders and blocks and things like that, your bending moment diagrams, things like that, they're very simple, straightforward to do by hand. When you start getting to the part that's on the right-hand side of the screen, the more complex the shape becomes, or the more complex the part becomes, it's not as easy to do those hand calculations, and it's also not as accurate because you're making a lot of assumptions there. And in order to analyze that complex shape, what we end up doing by hand is actually breaking that down into simple or more simple shapes. So for example, that cylinder at the top or the bottom base could be assumed to be a rectangular block, let's say. So when you start getting into the more complex shapes, we are in need of a better method. So one of the things that I want to talk about is by breaking those complex shapes down into smaller shapes or what we would actually call elements, it makes it a little bit easier. And a good analogy of this would be to compute the area of that shape on the left-hand side of the screen. What we can do is break that down into shapes that we're familiar with, and the area of a square is very easy. And what you see on the top row there is we didn't break it down quite enough. So what you have to do to improve the accuracy of that is actually break it down into even smaller squares. This essentially is the fundamental basis of finite element analysis. By breaking this area into squares, those are the elements. So it allows us to actually do very complex differential equations on small chunks of the larger shape. So with that being said, finite element analysis, or FEA, is a numerical technique for solving engineering problems. So what we see there is we see a cantilevered beam okay, with a force on the right-hand side and a fixture on the left. To solve that, ultimately that is truly a continuous problem. But right below that is what we see, or how we divided that into these smaller shapes. And from that we can do all those complex differential equations across each one of those shapes from the force to the fixture to gain out then stresses, displacements, and so on. So the real crux of this, or the real component that finite element has, is what we call the mesh. So as we divide our geometry into these pieces, or into these shapes, those are what we call elements, and that's actually what is called meshing. So you see on the left-hand side there that that bevel gear, that was divided into what we call elements. And on the right-hand side, you see that pyramidal shape, or tetrahedral, or tetrahedron. That is actually what we divide our geometry into. At each corner of that shape is what we call a node. And a node is what connects all of the tetrahedrons together. So they actually share those nodal points in between them. So each element is a simple solid, and the elements then again are connected by those nodes. And that's what allows us to actually do the equations or calculations on one element and kind of march our way across the entire structure. So at this point we really want to talk about designing with simulation. And there's really 4 simple steps to simulation. Very first one, and we all learn this in school, is what we call the free body diagram. It's really coming up with what is the realistic loading and fixturing of the component, in its application. So in this case, the component that we're going to be looking at, where you see the green arrows, those places on that structure would be bolted. Now we're going to assume that they're fully fixed just to make it more of a worst case scenario, but you can handle those as though they were truly bolted, so they would be allowed to rotate radially there. We're going to apply 1,200 pounds of force to that upper mount where the strut would connect into the suspension. So we're simulating basically a side load on this component. From there, the next step is to mesh or discretize that volume into those simple or easier shapes to calculate. And that's what you see on the left-hand side. Step number 3 really is to analyze, or let the software, should I say, analyze that or solve those equations across the geometry. And the 4th step is to actually interpret the results. What are we seeing, and how does this help us? So what I want to do at this point is jump into SOLIDWORKS, where we have that component. Now I spoke a little bit earlier about the fact that simulation is a gold partner, and ultimately right now is part of SOLIDWORKS. And like any other add-in inside of SOLIDWORKS, you can turn on simulation just by going to the options and checking simulation on. Everybody should be familiar with, if you've used SOLIDWORKS, to the command manager at the top. We end up with a simulation tab on this command manager. Now what I want to do is start what we call a new study. If you're familiar with the newer Excel, how Excel has workbooks across the bottom of the screen, each study creates a tab across the bottom of the screen. So I'm just going to call this static and 1,200 pound load. Now on the left hand side here, for the different types of studies, we cover a very wide range of types of studies that we can handle. Static, or linear static should I say, just means that our materials are assumed to be linear, so they do not go beyond yield, and we're assuming it's static, it's fixed, it's not moving, or a moving component. We also handle frequency, buckling, thermal analysis, drop tests, fatigue, nonlinear, linear dynamic, nonlinear meaning either the material is nonlinear like a rubber or a plastic. You're taking a linear material beyond yield, so it would be like a work hardening type scenario, or a nonlinear movement, so a large displacement or a large movement of the component. Linear dynamic would be your random vibration testing, your harmonic loading scenarios, and then we also offer a pressure vessel design to the ASME code. What we're going to deal with today is just the standard static linear analysis. So as I create this study, what we're going to see is it splits my feature manager on the left-hand side, and we have what we call the simulation manager. You can also see that my study started a tab down here at the bottom that is static 1,200 pound load. One of the benefits of the fact that this is inside of SOLIDWORKS is I had 1020 steel applied to the part. So I went in and I already applied the material to the part as I was designing it. That carries over into simulation. I will show you that we can actually change that material very quickly right after we run this run. So we started the study. The next step is really our free body diagram, or our fixtures and our loading. It's as simple as either coming up here to fixtures and loads, or everything can be ran as a right click off of this simulation manager. So if I right click, I can choose fixed geometry. Simulation gives a very good, clear, and concise preview of what's happening with a fixed geometry. It's basically saying that that green face is fully fixed, it's immovable, and that all the rest of the structure will be moving. We also have what we would call a roller slider, where it can move planar. We can deal with fixed hinges, and we have a lot of additional advanced fixtures. For this, again, we're going to be looking at what I would consider to be worst case scenario. So everywhere that this component is bolted together, we're saying that it will not slip and it will not move at all. So I'm just going to pick these faces to say that they are immovable. They cannot translate in the X, Y, and Z direction. The other thing to note here is it doesn't have to be a face. I could fix the entire component, which wouldn't make sense in this option. I could do just an edge or a vertex if I chose. So we have our fixtures. The next step is to add our loads. Now we can do forces, torques, pressures. We can add a gravity load if we're concerned with self-weight of the structure, centrifugal bearing loads, thermal loads, so temperature loads, and we can also couple with our flow simulation, our CFD package, to bring in thermal and flow effects from that as well. For this case, we're going to add a specific or simple force to this, and I'm going to apply it to these two components where the strut connects through that bolted connection. I want to do this, though, however, in a selected direction, and we're going to do it normal to the front plane. This is going to be 1,200 pounds. Now, one of the benefits here is we can see an on-the-screen indication of which direction that force is going. So we want that in this direction. And I also want to do per item. So I'm actually applying 1,200 pounds to each one of these faces. If I did total, it would divide that out evenly based on the area. So we have our force. We have our fixture. So our free body diagram is finished. Let's look at discretizing or meshing this component. It's as simple as right-clicking on the mesh folder and saying Create Mesh. Now we have a lot of meshing options that go above and beyond what the default mesher does. However, with the default mesher, we end up with a very good depiction of what the geometry is. So what you're going to see is as we go through and mesh this, we divided this component into those tetrahedral elements. And what you're really looking for here is that the structure looks like what the structure did in the CAD geometry. We're really representing this by a combination of all these tetrahedral elements. So this looks pretty good. The next step is to analyze this analysis. We can either select Run up here, or again, off of a right click, I can choose Run here. So we're going to go ahead and allow the solver to run through. Basically, it was calculating all of those equations across all of the elements, And just a quick note, if I look at the details of this mesh, each one of those nodal points has 3 equations being solved, basically a translation of the x, y, and z. So what you can do is look at the total number of nodes and multiply that by 3 to get the total number of equations that were being solved. And essentially, what we're looking at here is 10,205 nodes. So that quickly we just solved 30,000 equations. Or should I say the software solved 30,000 equations that quickly to give us the answers that we need. So the yield strength of this 1020 steel is 50,000 psi. What we're seeing here is our maximum von Mises stress is 20,000. This should actually bring up a very familiar term or comparison, which is factor of safety, which is actually your yield strength compared to your actual. And we actually have a factor of safety plot. So I can define a factor of safety plot on this component, and we want to see the entire factor of safety distribution. And what we see with this is that we have a minimum factor of safety of 2.51. So in general, we want to stay above 2 for a very, very conservative, very safe design. We're at a 2.51 here. So we know our design is safe as is. We go back to our stress plot. Let's just investigate some of the things that we can look at here with our stress. If I edit the definition of this guy, we don't have to just look at von Mises stress. We can also look at our normal stresses in the x, y, or z, our shear stresses, our principal stresses as well, stress intensity. Let's go ahead and look at the normal stress in the x for this. And if I put in my push pin, just like in SOLIDWORKS, I can leave open this dialog and simply switch between these plots. So I can see my stress, my normal stress in the x, my normal stress in the y, as well as my normal stress in the z. Let's go ahead and switch this back to von Mises for right now. And let's animate this. Now one of the things that the animation offers here is the fact that we can just kind of do a sanity check on our loading. So we would expect with a 1,200-pound load on each one of those bolted surfaces that this upper arm here would move towards the left of the screen, which is actually what we're seeing out of this animation. So we have a sanity check for our boundary conditions with that animation. Now just to make a note of this, the deformation scale of this plot is 133 times what the true deformation is. So if I switch this to true scale and I select OK, we're going to see that that is a lot less drastic. And actually, the other plot that we can look at is displacement. I don't know about you, but I really do not like scientific notation. So if I double click on my legend here, I can change that to floating and increase my number of decimal places. So we actually see 0.011 inches of actual displacement per that loading. So our design is actually very stout for us. Another thing that we can look at here with our stress plot, and I like this option quite a bit, is something that's called ISO clipping. So let's say, my design is only at 20,000. I have a factor of safety of roughly 2.5, but I'm still concerned with everything that is above 14,000 psi. And when I select OK, this narrows down where my stress is above 14,000 psi. Or if I reverse that, this is everything that's below 14,000. So it allows me to narrow down those areas very quickly. The last plot that I want to show you is a plot that I use all the time, and it's called a design insight plot. Because our main goal here is not to say, okay, I did my design, it meets all my criteria, let's go ahead and put it into production. My goal here is to try to take out weight, take out manufacturing cost, and optimize this design as I run through it. That's why you do multiple design iterations. What the design insight plot allows me to do is actually see from the loading to the fixtures how that load travels through the structure. So the areas that are in blue is really where the load is being transferred or pushed through the structure. So any areas that are in or are essentially clear, we can go in and add additional cuts, or we could remove material from here. Maybe thin out this arm a little bit. So a lot of options here. The two things that I'm going to do is I'm going to go ahead and add a cut in this area, and I'm also going to change the radius of this fillet here as well. So when I select OK, my design insight plot actually stays up. What I can do with this, I can either stay in the same study or I can create a new study. And actually, what I'm going to do is create a new study. And I just want to show you how simple this is. We already went through and made sure that we added our fixtures, we added our loads, our free body diagram, we did our mesh. If I start a new study up here, it's going to be static, and we're going to call this Design Change 1. Our material carried over, but our free body diagram or our forces and loads did not, or fixtures didn't carry over, and our mesh didn't. However, we can go back to our original study. I'm going to Control Select these components, and I can simply drag and drop those over top of Design Change 1. And what we see is our fixtures updated and our force updated. I'm actually going to unsuppress this cutout here, so we end up with a cut. And then I'm also going to go in and I'm going to add a fillet to this component. So between these two faces, and let's make that a, let's say 15 millimeter fillet. So we made those two design changes to this component, so our cut and then our fillet change. We can go ahead and remesh this anytime that the geometry changes, the physical geometry changes, a new mesh is required. And the reason being is, if we use the old mesh, this hole wouldn't be seen, nor would that fillet be changed. Let's go ahead and rerun this analysis, or this one, or analyze it, and see what we get out of this. We're still right around 20,000 PSI, so our factor of safety is still at a 2.5, roughly. And what we see is, based on that design insight plot, we made the correct decision. We reduced weight out of this component by cutting the hole through and removing that, or making that fillet larger in areas that were not affected by the load. So it's a very good plot for seeing how can I make future changes to this. So we just did another, or a new virtual prototype within a matter of minutes, and we're getting good feedback that we're on the right path for our design changes. The last thing that I want to show you that we can do is, what if we want to change the material? So we like the cut and we like the fillet, but we want to change the material of the structure. Instead of starting a new study and duplicating or pulling over those already existing boundary conditions, what I'm going to do is actually duplicate the entire study. So I can change this to Design Change 2, and from doing that, what I can do is change the material itself. So if I do Apply and Edit Material, I can change my material directly in this new study. So instead of 1020, let's say we switch to 304 steel. So my yield strength is 30,000. If I select Apply, I change my material, my fixtures came over, my mesh came over. All I have to do is reanalyze this. So we see that our stress stayed the same, and the reason for that is we're really changing very little about the material other than the fact that the elastic modulus stayed the same, so our stress is going to be about the same, but our yield has changed. If we go back in here to our factor of safety plot, because our yield changed, what you're going to see here is that my factor of safety dropped to a 1.44. We can actually duplicate this one more time, and I'm going to call this Change 3. You could also rename these per material that you tried or per loading that you've tried. We could increase the loading as well. I'm going to go back in and just on a whim here, change this from steel to aluminum. And let's say it's a 6061 T6 aluminum. So our yield is actually 39,000, but our elastic modulus is different. So we may end up with different deflections out of this. So let's go ahead and rerun that analysis and see what we gain out of it. Our stress is roughly about the same. Our yield has changed. And our displacement is different. And the reason for that is we changed material. So if I switch to floating and increase this, we can see that our deflection changed with the aluminum. Now the entire weight of the structure is probably less. This may be the better route to go if the aluminum's less cost than the steel. So the key thing here is very, very quickly, easily, and effectively, I've now tried 4 different design paths for this exact same steering or suspension component. So hopefully this really illustrated or kind of shed some light on the fact that virtual prototyping or virtual testing is an effective tool throughout your design process. Let me go ahead and switch back to the PowerPoint here. So in summary, again, what I hope this webinar kind of illustrated and showcases the fact that we can design better products while designing products better. Okay, so it's very effective. It's very fast. So we can get to market faster by doing virtual prototyping as opposed to actually physically creating it and then testing it. And we can also design quality products while designing more quality into the products.